Okay, so here's where we were last time. We were talking about how to use this really weird construction of matrix exponentials to solve differential equations. So a seemingly very artificial, made up construction, and yet we're solving equations with it, which seems crazy right up until the point where you realize that, well, isn't that kind of what happened when we were looking at complex numbers, right? I mean, e to the power of an imaginary number, that's crazy talk. We make up a seemingly arbitrary, literally not real mathematical construction, and yet it helped us solve differential equations. Okay. All right. So here we are in this specific case. This is the formula you need to make sure that you know for how to use matrix exponentials to apply to Jordan basis vectors. Very importantly, this only applies to Jordan basis vectors. Right? And in this very specific way. So this assumes that you have a specific basic Jordan block, that you are looking to apply the matrix exponential to one of the vectors, one of the basis vectors corresponding to that block. And by corresponding, I mean that block, of course, intersects certain columns. Those columns tell us about the images of certain basis vectors. Furthermore, it pertains only to this little subset, you might say sub-basis, if you prefer, of vectors. You don't jump over into what's going on in other blocks, right? So we're confined to the basis vectors in that block. Okay, and with all of that said, our formula was, like I say, like this. And we apply that to the Jordan basis. Now, in this particular differential equation, the matrix, I gave you a Jordanization of that matrix. All right, so that's free arithmetic. Now, it is, again, on you to interpret this arithmetic appropriately and, think about which matrices represent a transformation with respect to what basis, to infer correctly that this matrix is the one whose columns are the Jordan basis. And once you have those Jordan basis vectors, then again, it's just a matter of plugging those in to this equation, and out come these formulas, and that's our fundamental set. Okay, so we did a lot of details of that last time. I won't reproduce all those details. I do want to remind you, and this is the last thing that we did with this last time, that again, this little formula, how we apply this formula and which basis vectors it relates to, specifically the basis vectors that correspond to a specific Jordan block. So if you want to know, for example, here's a matrix that has multiple basic Jordan blocks, unlike the previous example that had only one. If you would like to know what the matrix exponential e to the xa does to the vector v4, for example. Well, v4, let's see, where is that? Here's v4. Which block does that correspond to? Well, let's sort of mark it up here. This first block corresponds to the first two columns, which correspond to the first two basis vectors. This second block corresponds to what you might call columns 3 and 4. That corresponds then to the third and fourth basis vectors. This last block corresponds to column 5, and therefore this fifth vector. So if you want to know what the matrix exponential does to V4, we are thinking about that green second, if you will, basic Jordan block. That's the block to which we apply the formula. This is the diagram of what A minus lambda I does to those Jordan basis vectors. Furthermore, notice, for that block, the eigenvalue is 4. So A minus lambda I is specifically A minus 4I. I think I have this one written down here. Applying this formula to V4 gives us that. Okay. Note, very importantly, the process stops when you get to the eigenvector. We stop when you get to that eigenvector, V3. Right? V3 is an eigenvector, so you stop there. Said differently, as you're moving back through the basis vectors, here you stop when you get to the left edge, if you prefer, or if you're thinking of it this way, over here you stop when you get to, again, that eigenvector. Okay. All right, pause for questions. Anybody have any questions about this? Okay. All right, so this is a good method to have in your toolbox. I encourage you to use it when you can, right? When the opportunity permits. I want to note though that being able to use this method does not mean that you'll never need to use the other methods. Those other methods are very useful in many contexts. Other contexts where this might not apply. As a general sort of, strategy of construction, the idea of a change of basis applies very broadly in many ways, in many areas. The ideas of a conjugation and, similarity by way, so you create an equivalence relation by way of conjugations, which led us to similarities. That concept of conjugation shows up very naturally and powerfully in many other areas. So, as a strategy, arguably, our older methods are more important. But this is, for this narrow application of solving these differential equations, this is pretty awesome. Hard to beat. Okay. Okay, so we have spent 2 sections of the book considering the homogeneous case. Right? So we were looking at systems of differential equations, and the first thing, obviously, you're going to consider is the homogeneous case. That was the first thing that we considered back in Chapter 4. Remember, we're seeing strong analogies between what happened in Chapter 4 and what's happening here in Chapter 6. So, first we got to set up some framework, some theorems, big picture strategy. Then we consider the homogeneous case. Again, weirdly, we had to break it down into 2 homogeneous cases here in Chapter 6 because of the whole diagonalizable, not diagonalizable. It's pretty different in those 2 cases, whereas in Chapter 4, we just did it all in one section. Okay. So very naturally then, just like in Chapter 4, the next thing to do is the non-homogeneous case. Here we are again, non-homogeneous case. It all comes down to how do you find a particular solution. We know our general solution is going to be any one particular solution that you can find by any means, by hook or by crook. Add your homogeneous solutions that we've already discussed at great length. That gives you your general solution. So, what remains? How do you find one particular solution? Okay, I'm going to give you a little bit of discussion of the single variable version of this first, just for the purposes of setting up a template, a pattern that we're going to then copy when we get into the vector case in just a few minutes. Roughly speaking, so here's our differential equation. Now notice we are viewing A here as being a function. So this isn't the sort of 4.2 kind of stuff that we considered, or that kind of thing. So a quick observation: the homogeneous equation is solved by that function. Clever move. And it works. How nice. Okay. So that function is what we're going to call a, you could call it a, you can, by the way, you can think of it as being this one or that one, whatever. This by itself is a basis for our set of homogeneous solutions. You might call it a fundamental solution, I suppose. Right, reasonable thing to call it. It's just one. We're talking about a one-dimensional vector space, but nevertheless. So, how are we going to find the particular solution? This is a shot in the dark that happens to work very nicely. Okay, so the next step that I'm going to make is what at this time I have to confess is wild speculation, and it's just going to turn out that it works great. All right, so here's the idea. We know that if we consider the homogeneous case, we know we have a solution. right? This function here that we're calling m, that goes into our homogeneous equation and works just fine. Here's another way to say that. You might say that this function m kind of balances both sides of this equation. Furthermore, if I multiply by a constant, let's say if I multiply by some constant value c, still works, right? Doesn't matter what that constant is. Okay, so, the non-homogeneous question says, what if you have this extra term here? Well, all of a sudden, this is no longer putting the equation in balance. There's extra stuff over on this side. So the equation is now out of balance. And what we're going to try to do, our hope here, is to figure out what might we do to the thing that previously had it in balance. What might we do to that? How might we tweak this a little bit to hopefully retweak the balance? That's the hope. Wild speculation, right? I mean, I have no particular reason to believe, no pun intended, no clear reason to believe why it is that this should necessarily work. But hopefully, optimistically, we proceed. So what we're going to do is, instead of multiplying m times a constant, let's multiply m by another function and hope that we can figure out what this other function might be. That by multiplying this by a function, that's going to mess with the balance, and hopefully we can get it to mess with our balance the same exact way that this g is messing with our balance. So that's the hope, and turns out it works great. Here's the idea. We're going to take that new sort of trial function. We're going to plug it into our differential equation, which gives you this. Product rule. Right, no big deal. Then we look at this equation, and you notice in this equation that we see some familiar terms, right? So, in fact, right here is the balance that we previously had. That's our previous balance. M prime equals AM. That's that right there. So you can kind of see, having multiplied our function by v, what it does is it creates this new term. Right here, this guy. So if I want to regain the balance, that was put out of balance by g, multiplying by v gives me this new term here. Regaining the balance would come by simply making those two things equal to each other. Or said differently, I know m prime is am, cancel those terms, and I end up with mv prime equals g. And then solve for v. That's a little bit of algebra. And you get to keep in mind what v was. V was our tweak. Right? Once you get v, you multiply by m, and that's your solution. So following that procedure, solve for v. Solve for v, multiply v by m, and here's your solution. Okay, this works just fine. You don't have to go through this process every time. You can just write this down as a solution. This works. If you know that homogeneous solution m, right? You know that, and if you are given a g in your non-homogeneous equation, it's just a matter of plugging in and computing this integral. Okay. All right. So now that's the sort of the scalar version of what we're looking at. Now we're going to consider the vector case. All right. So here's a vector equation. This is the homogeneous version of it. We know what the fundamental set of solutions is. We know how to write that as a solution matrix. You may recall we called this M. And by the way, there's the giveaway of why I called this solution M, because it's our fundamental solution. This is the thing that I'm going to want to tweak in the hopes of finding a particular solution. Okay. Okay, so now, again, let's consider, I know that the homogeneous solutions look like this. Any one of these functions solves the homogeneous equation. Furthermore, I know that I could take any linear combinations of these. So, for example, I could multiply by some constant vector. Now, in the previous case, we had observed that if you multiply by a constant scalar, right, that this still works. Here we're multiplying by a constant vector, which is just a fancy way of saying we're going to take linear combinations of our known homogeneous solutions. Okay. Just like before, we're going to speculate wildly that, hey, if your equation all of a sudden it's out of balance because of some new extra term, hey, maybe if I do something over here to kick this out of balance a little bit, maybe I can get those to cancel. So I'm going to speculate just like we did previously. Instead of multiplying m by a constant vector, let's multiply it by a vector function. Again, no clear reason to believe why this ought to work, but hey, it kind of, I mean, something like this worked in the scalar case, so hey, let's give it a try. So we're going to consider this as our test function. We're going to plug it in to this equation. Here's what you get. Notice the pattern. This is very, very similar to the scalar case. Product rule. Again, same product rules before. Again, you'll recognize some terms. These terms. There is something a little bit awkward about this. I say m prime is equal to am. Well, is that really true? Is m prime equal to am? I know that these functions are solutions to that equation, but the thing is, it was the columns, specifically. The columns of this matrix solve that equation. Right? And then, hopefully it's an easy sale, but if the columns satisfy that equation, notice that both sides of the equation apply separately to individual columns. Right? How do you multiply A times M? Well, you multiply A individually times all the columns. How do you take a derivative of a matrix? Well, you take the derivatives individually of all of the columns. Right? And so because that equation is true for M one column at a time, it's also true for the whole matrix M. So that's just a little that's a section 1.2 exercise. You can persuade yourself. Anyway, those cancel. What's left over is this. Again, our hope was to solve for, what is this V thing? What is this tweak that we can do to our existing homogeneous solutions? So we solve for V. And once you know V, don't forget our actual particular solution is going to be V times M. And so we get this formula. And you might recognize the formula. Structurally, it looks just like the formula for the scalar case. Right? So this will do it. This will find particular solutions for you. And that's kind of nice. Okay. Anybody have any questions so far? Plug and chug. All right. Now, there's the bad news. There's a lot of chug in this plug and chug. I'm going to show you some examples of how to use this formula, mostly to persuade you of how inconvenient this formula is. Even though, again, hey, it's a formula and it works and it gives us the answer we're looking for. This is a very substantial cost. So here we go. Here is an example. Let's look at this non-homogeneous equation. Now, you'll recognize the homogeneous part here. There's our homogeneous part. We've solved that homogeneous part. I mean, I use that matrix a lot, right? Because we know the eigenvalues, we know the eigenvectors, and it's nice to have something familiar and then not have to reproduce arithmetic that's morally equivalent. Okay, so we know that these are the solutions. Therefore, we know this is our solution matrix M. Okay. All right. Well, with that, notice my formula says you've got to take that M, you got to invert that matrix, you got to multiply by the G vector, you got to take the antiderivative, and then you got to multiply back by the M matrix. Okay, so this you can see the tedium stacking up here. I'm going to let y'all walk through the details of this tedium. I think this is an important exercise for y'all to fill in all of the blanks on this tedium. If you want to use this formula, say on an exam or something, you need to know how much tedium you're up against. So please fill in all of these blanks. But here they are, just as on the large scale. Inverting the matrix gives you this. Make sure you can do that. Multiplying by G. Well, it's a matrix times a vector. G was given. Here it is. Multiplying by G. Here, let me zoom out so I don't have to scroll. Multiplying M inverse times G gives you that. Okay. Next step. Take an antiderivative of both sides. Okay, now it's starting to get a little annoying, right? The antiderivative of this. Oh, we're going to be taking antiderivatives of both of the components, each of the components individually. Each one of these is an integration by parts problem, which is highly undesirable, right? And I'm sure y'all remember from Calc 2 classes, integration by parts. I mean, it's not that bad. It's doable, right? But it's a certain amount of tedium to it. And here you have to do two of them. Okay. All right. Details for y'all. There's what it ends up being. Oh, and then I guess it simplifies. No, I guess I left it like that. Okay. And having done the antiderivative, you then have to multiply back times this M matrix. So lots of effort, and here's your final solution, and that is a particular solution, and it works just fine. Everybody on board? All right. Here's another one. Now, y'all will probably recognize this first step. This non-homogeneous equation, we look at the right-hand side. That right-hand side has trig in it. And trig tends to be a little bit harder to work with algebraically, right? We've all seen examples. So I'm going to do the same trick that we did back in Chapter 4. I'm going to say, how about let's instead consider this associated complex system. By associated, I mean notice that this is the real portion of that, right? If I can solve this complex system, which I claim is much easier, then this solution, I'm just going to have to, at the very end, once I've found this z, I'll just have to look at the real portion, and that will give me the y that I'm looking for. It's the same move that we pulled back in Chapter 4. So here we go again. And again, it's just a matter of applying the formula. By the way, notice that our new equation here, z prime equals that same matrix times z. We already know the homogeneous solutions. So we already know the M matrix. We already know the M inverse matrix. It's the exact same M, therefore the exact same M inverse. So we kind of get to skip a couple of steps. But anyway, next we have to multiply by G. There's our G. Multiply M inverse times G. That gives you this. It's not that bad. Antiderivatives. It's not that bad. Right? Look at this. Taking an antiderivative of, they're just exponentials. Right? That's as given how ugly integrals can get, that's pretty desirable. Right? So those antiderivatives turn into this. Again, now I'm skipping all the algebra here because y'all are good at algebra. So anyway, but make sure that you follow through and that you can do all these little steps of algebra. That is going to be essential in doing these problems. Having done the antiderivatives, that very last step, multiply back by the M matrix, and here you go. This is your Z solution. Now, of course, this is not our actual solution that we're interested in. This is the complex solution. We wanted the solution to the original real version of the equation, so we need to look at the real portion of this solution and taking the real portion. Again, now there's a certain amount of complex algebra there. Make sure that you can do this complex algebra, but this is the real portion. And just strategically, let me point out how that goes. Real times real gives you real, but also imaginary times imaginary also gives you real as well. We don't have to work out the imaginary part. We don't have to do, real times imaginary and imaginary times real. That would give us the imaginary portion. We don't need the imaginary portion. We just need the real portion. So this is all we have to write down. Okay. All right. And there's a solution. How are we doing? Is everybody on board? Okay, real quick, I want to point out what the alternative would have been on this question. Let's go back up to here. Remember, we made this early decision to, I don't want to deal with the cosine. I'm scared of the cosine, algebraically. I would rather deal with exponentials, even if they're complex exponentials. I'd rather exponentials than cosines. Okay, let's suppose we hadn't done that. Okay, let's suppose that we decided to go straight from here. And let's see how this would play out differently. This would then be cosine x. Right there. That would make this instead negative 2/5 e to the negative 4x cosine x. And let's see here, 1/5 e to the 1x cosine x. Doesn't look that bad until you get to the next step and realize, yeah, so this thing that I just wrote down there, that thing, that's what we're going to have to take an antiderivative of. And this is where it becomes highly, highly undesirable. Do y'all remember how to take antiderivatives of these kinds of functions? Really annoying. It's integration by parts, but you have to do integration by parts twice for each one, thus opening yourself up to liability of possible minus sign oopses, and there's several fractions involved here, and it just seems like there's lots of potential for that to go wrong. Right? At a minimum, it's 4 integration by parts applications, and it's just undesirable. Yeah. So anyway, I think it's good to point this out. I want you to see, what did we skip? What did we bypass at the cost of a little bit of complex arithmetic? Yeah, I had to deal with some complex numbers in my denominator here. It's not that bad. And at that very small cost, I got to get rid of 4 integration by parts problems, and instead did 2 integrals of easy exponentials. It's just exponentials, world's easiest integrals. So I think it's a really good deal. So for your consideration, I think this is a really nice trick. Okay, how are we doing? Okay. All right, now let's go back to the previous example. There's something a little unsettling about this previous example. The question in this first example that we did, the matrix is full of constants. The right-hand side is first-order polynomials, monomials, in fact. It's all pretty basic, right? Now let's look at the answer to the question. The answer to that first application that we did is all pretty basic. It's first-order polynomials. There's some kind of annoying fractions, but whatever. So, essentially, easy question, easy answer. And yet, our solution involved lots and lots of exponentials all over the place. Right? Integration by parts with exponentials, So what's the deal with all those exponentials? How come we have to deal with so many exponentials? There were no exponentials in the question. There were no exponentials in the answer. Kind of makes you wonder if maybe the exponentials don't really kind of need to be there. Perhaps. Right? So that's kind of true, actually. So now notice this formula that we have, that we were using, this formula, works. That doesn't mean that it's the only way to do it. And it doesn't mean that it's necessary. Right? So here's a different way that we could go about trying to answer that question. Let's see here. Yeah. This question here, same question that we answered by going through that whole tedious process. Let's just try to guess. And by the way, the analogy to Chapter 4 continues. Right? So in Chapter 4, how did we find particular solutions? We guessed, right? Educated guesses, undetermined coefficients. We guessed with fudge factors that we gave the lofty name of undetermined coefficients, but it's really a guess with a fudge factor. Right? We looked at the form of the equations. We speculated on what kinds of terms show up when you do. When you're taking derivatives of the kinds of functions that we think might be showing up here, what other kinds of terms show up? And let's just kind of put together a little story that has the potential for everything to balance out. And it worked great back in section 4.3, undetermined coefficients. So we're going to try the same thing here. I'm going to try. Based on looking at this right-hand side, I speculate, we have a constant vector times x. This probably has a constant vector times x in it too, because something's got to balance out that green term. Okay, but the thing is, if that term is in y, then when I take the derivative over here, there's going to be a constant vector on the left. Well, if I only put this bx vector, there's no constant term on the right. So I'm going to also put in now a constant vector, and this constant vector a as part of the right-hand side. Hopefully, however it works out, I'll be able to make that balance with the b vector that will show up on the left as part of y prime, etc. Right? And then you got to sort of continue speculating. Yeah, but what about the derivative of this constant vector? And of course that's 0, so the process sort of terminates quickly here. But just like we did in 4.3, speculating about what kinds of terms show up when you take derivatives gives us a candidate form to possibly be our solution. Notice we have in here our fudge factors, aka our undetermined coefficients, right? And okay, fine, we just need to solve for those undetermined coefficients, so we're going to take this, we're going to shove this back into that equation and see what comes out, which is this. And now we just have to try to figure out the a vector, little a vector, and the little b vector. Okay. All right. Okay, so a good way to do this is to notice that this expression involving x, if this is always going to equal, both sides are always equal, then the constant terms have to equal to each other, and the x coefficients have to equal to each other. And that's just kind of how polynomials work, right? So it's just like we've done on similar occasions with scalar polynomials. So looking at the constant terms, let's see here, the constant terms are that and that, which give me that equation. And now let's look at the coefficients of x. I have that, and that gives me that equation. So yeah, we started off with one vector equation, and now I'm going to rewrite this as two individual equations. And now it's just a pretty easy matter of solving. You do have to think strategically about how you solve these. Don't try to solve the yellow equation first, right? I can't solve for A, because in order to solve for A, I would have to know B, and I don't know B yet. So of course, the very first thing we do is we solve for B in that equation, and once you know B, which is easy to do. Once you know B, then you can go back and solve for A, like that. And you might recognize, right, with this A and this B, our speculated solution then becomes exactly what we had about several pages back when we went through that whole tedious process with integration by parts and all that nonsense, right? You got the same answer by making reasonably educated guessing with fudge factors and then, scheming about how to make those fudge factors work out. So, y'all get to decide, which of these methods would you like to do on an exam? Would you like to do this method right here, which is pretty quick and easy in this case? Look how nicely it worked out. It's not that bad. No integrals at all. The derivatives were easy derivatives. Worst part about this is I had to invert that matrix. Right? This is a pretty straightforward, pretty desirable solution. Or would you perhaps instead prefer to go through this whole process here where it looks about the same length on the page here, but I have swept an enormous amount of I've swept a substantial amount of algebra under the rug, left as exercises for y'all to work out, all this integration by parts, for example. Right? So the choice is yours. Now you can see I'm pushing pretty heavily in favor of do it the easy way, right? I do want to confess, though, to a cost. This method here, the cost is paid, up front, in that you sort of know that you're going to have to do a lot of algebra. The thing is, this will work. This will definitely give you a right answer. The problem with this method is you are guessing. And not only might your guess not be, the right form of guess, it is also possible that it still won't work out. Even with a plausible guess, it just might not work out. For example, what if, you get down to this point and you realize that, to solve for B, I'm going to have to invert the matrix A. What if A is not invertible? Excuse me. You could be forgiven for not having noticed at the start of the question that the invertibility of the matrix A was going to be necessary. It doesn't leap off the page at you, right? You get halfway through the problem before you realize that, this thing better be invertible. And if it's not, then you probably can't make this work. Conceivably, you might get lucky, and even though the matrix is not invertible, it might still be that this is solvable, right? Maybe. But not necessarily. So there's a little bit of a risk there. Honestly, most of the time it works out. So again, I encourage you to do it this way, but you do have the choice. Okay. All right, here's another example. Just a structurally different example and structurally different concern that comes up after the fact. Let's look at this equation. And let's take a section 4.3 kind of strategy on how might we speculate on the solution to this. Let's see here. We have an exponential times a constant vector on the right. What sort of guess should I make in the hopes of getting an exponential times a constant vector over here? Well, how about how about an exponential times a constant vector? Right? An exponential times a constant vector, if that were my solution, when you multiply it by this matrix, it's going to be an exponential times a different vector. But there's the potential that I could make those balance out. Things are looking good. Oh, wait a minute. What about the derivative over here? When you take the derivative of an exponential times a constant vector, you get another exponential times a constant vector, right? So everything is coming up exponential times constant. There's strong potential, it would seem, for this to work out. So if we plug that in and then just try to work out our fudge factor, right? Our fudge factor here is the A vector. Let's just try to figure out what that A vector has to be. And the equation turns into this. Note the the common factor of this exponential cancels. Move a couple of terms around, and what you end up with is this. And so that's how you solve for your A vector. Whatever this thing is on the right, whatever that vector is, that's multiplied by the exponential. Solve this equation for your A vector. Well, that's nice. And usually, that'll work out. And of course, not always, right? So what's the circumstance where this wouldn't work out? Well, what if A minus Ri is not invertible, right? If this matrix that I need to, through which I need to solve for A, if this matrix is singular, then I probably don't have a solution here. And this didn't work. As it turns out, and this is just kind of weird, but another way to say if A minus Ri is singular, another way to say that is if R is an eigenvalue. Isn't that sort of unexpected? But that's the worry, right? Our worry here is that R might be an eigenvalue. How are we doing? Okay. All right. So what would we do in this circumstance if it were? I mean, if R is not an eigenvalue, yeah, solve for A, no big deal, sits straight up. But what if it is? So let's look at this equation. Now it's still exponential times constant vector, just like the previous example. You'll recognize this matrix, though. That's our old friend. We know the eigenvectors, we know the eigenvalues, and this is an eigenvalue, right? So that has come to pass in this new example, and if we were to just plug in the form that we did previously, we would kind of expect to probably not be able to get solutions. Okay. So what do we do? I have to point out here that this is a situation where the analogy between chapters 4 and 6 breaks down. In chapter 4, in section 4.3, at some point, we kind of quit guessing, right? We wrote down this great big theorem, this amazing theorem, in fact, that says that, hey, here's a tremendously broad category of possible right-hand sides. And if that's your right-hand side, anything of this form, then there's a little algorithm, follow the algorithm, weird algorithm, but follow the little weird algorithm, and out comes a guess that is guaranteed to work. Right? That was fantastic. And unfortunately, it's just not that simple in this context. There's just too many different ways that things could be different in case. I suppose maybe you could conceivably write down this theorem, but it's just not worth the effort. It would be much uglier and not reasonable to work with. So we're a little bit out in the woods. We don't have this, this instruction that if we just follow the instruction and it'll all work out. Here we have to kind of guess. So I am going to guess. Previously, when we plugged in this, it worked unless we got unlucky, which we did here. How do you revise your guess? Throw in additional terms that have the potential to knock your imbalance back into balance. And notice that including this additional term here. In fact, I should highlight a little bit differently. This additional term here. So exponential times constant vector times x. That additional term, when you take its derivative, gives you product rule, so it gives you two terms. Among them, it gives you another exponential times constant vector, right? So there's potential. This second term that I have highlighted in green here has the potential to give me additional flexibility to work with to maybe fix the previous problem. So it seems like a reasonable thing to try. And with that said, we take this, we plug it into the equation. We see what the equation turns into. Now, again, there's a bunch of algebra here. I'm going to let y'all work out that algebra. Again, I remind you, please do this. Please actually work out that algebra so that you are sure that you can reproduce this kind of thing if necessary on an exam. Anyway, it turns into this. Note the common non-zero factor in all the terms of this exponential. We get to factor that out. Again, let's separate out coefficients of x from coefficients of 1, right? Constant coefficients. And again, we have two separate equations to solve, right? This is sort of a familiar place. I need to find vectors a and b that make both of these equations work. Everybody good? Okay. We're not going to finish this example today. Let me make a couple of quick comments, though, about strategy, and then we'll finish the details next time. Notice that in these equations, there is a strong temptation to jump on this one on the left first. Because you see, singular matrix, homogeneous. I know that not only is there a solution, there are infinitely many solutions here, because I know this matrix is singular. And I've got infinitely many to choose from. Oh, my cup runneth over. I'll just pick one. I'll pick the easiest one that I can think of because I got options. That's a mistake. Don't just pick one. This B vector is playing another role. That B vector is over here. Right? So what we're going to try to do next time is to figure out how can I find a B vector that will, satisfy this equation in which I have a lot of flexibility. Thankfully, I have a lot of flexibility. But find that B in such a way that will make this equation solvable. Because over here, the singularity of this matrix is not our friend. Over here, the singularity is the problem. I have a non-homogeneous equation with a singular matrix. This solution might not exist at all. So we're going to try to do a balancing act next time to figure out how to make something, choose among the many options here that will allow for there to be a solution here. Details next time. Y'all have a great weekend. See you later.